So in this video we're looking at chemical bonding, but we're specifically going to look at covalent molecule shapes. So our learning intention is to discuss the different geometries of covalent molecules using VSEPR and construct them using model kits. So, to begin, covalent molecules consist of separate molecules whose geometry can be determined using a theory called valence shell electron pair repulsion theory, and that's simply referred to as VSEPR. And the shape of a covalent molecule depends on the number of electron pairs around the atom. So they arrange themselves so they are as far apart from each other as possible. And this is due to repulsion between the electron pairs. So the easiest way to look at this is to dive straight into some examples. So the first molecule we'll look at is beryllium chloride, and it has a chemical formula of BeCl2. Now, we know that beryllium chloride has two pairs of electrons around the central atom. Now, if we look at our structure down here, we can see that there is a lone pair of electrons on our chlorine. However, we ignore these because VSEPR only needs to consider the electrons that are around the central atom. So we can clearly see here that there is two pairs of electrons that are linked with our central atom. So to discover the geometry, a series of experiments is completed that you don't need to know about. The main thing you need to know is the result. And it found that beryllium chloride has a linear geometry. So that means that the bond angle in beryllium chloride is 180 degrees. So we can explain this 180 degree angle by saying that the two pairs of electrons, which are negatively charged, repel each other. So at an angle of 180 degrees, they are as far apart as possible. So basically, when they're 180 degrees away from each other, the repulsion between the electrons is minimized. So all molecules that have two electron pairs will be linear and have a bond angle of 180 degrees. Next, let's look at beryllium chloride. And beryllium chloride has three pairs of electrons around the central atom. Again, we remind you that the lone pairs in the chlorine are ignored in VSEPR because we only care about the electrons that are around the central atom. So in our diagram down here, we can clearly see that there is three pairs that we are worried about. So from experimentation, it was found that beryllium chloride has a geometry known as trigonal planar, and trigonal planar creates a bond angle of 120 degrees. So as we can see down here, the angle between each of our bonds is 120 degrees. So in this arrangement, the three pairs of electrons which repel each other are as far away from each other as possible, and all three pairs of electrons are in one plane. So basically, all molecules that have three pairs of electrons around their central atom will have a trigonal planar geometry which has a bond angle of 120 degrees. So next, let's look at methane. So methane is CH4, and we know that it has four pairs of electrons around the central atom. So we can see these four pairs of electrons around the central atom in our diagram here in the top right-hand corner. So methane is found to have a tetrahedral geometry, which is the shape of a tetrahedron, where the bond angle is 109.5. So by adopting this tetrahedral shape, the repulsion between the electron pairs is minimized. So we show this geometry by using wedges and dashes, where the wedges show that the CH bond is coming out of the page and the dash shows the CH bond going behind the page. And these two straight lines here indicate that these bonds are in the plane of the page. So in our example so far, we've just looked at bond pairs in the VSEPR model. So a modification to the theory was needed to deal with lone pairs. And it's important to remember that a lone pair is a pair of electrons in the outer energy level that is not involved in bonding. So the modification that was made states that the repulsion between two lone pairs in a molecule is greater than the repulsion between a lone pair and a bond pair, which in turn is greater than the repulsion between two bond pairs. but it might be easier to put this in a little flowchart for you. So lone pair is greater than lone pair is greater than bond pair. So the lone pair repulsion is the strongest, and the bond pair repulsion is the weakest. And as I said already, lone pairs are not involved in the bonding, so are closer to the nucleus than bond pairs. So lone pairs exert a greater force of repulsion on each other than bond pairs, which causes a slight difference in the bond angles from that expected if repulsion was the same for lone pairs and bond pairs. So let's try some examples. So let's begin with ammonia. Ammonia has a formula of NH3. Now we know that nitrogen is our central atom here, so nitrogen has 5 electrons in its outer shell. 3 hydrogen atoms then are needed to obtain a full octet, so the total number of electrons around the central atom will be 8 once this happens, and we'll have 4 pairs. So 4 pairs of electrons would predict a tetrahedral shape with a bond angle of 109.5. However, as we're going to see now, this is not the case because some of these electron pairs are lone pairs. So if we look at our structure here, we can see the 5 electrons around the central nitrogen atom. Now, the fact that the nitrogen will bond with 3 hydrogens to obtain a full octet, that means that 3 of these 5 electrons will be used in bonding, but the other 2 will not, which causes us to have a lone pair here. So we can see the nitrogen has a full octet due to the covalent bonding with the nitrogen, but the lone pair present causes a slight change in our bond angle. So the presence of the lone pair will distort our bond angle in ammonia to 107 degrees. And this bond angle is called a pyramidal geometry. And this occurs due to increased repulsion from the lone pair. So this lone pair are repelling against the bond pairs that are present in the ammonia to produce this pyramidal shape. So we predicted that it will be 109.5 with tetrahedral due to the 4 electron pairs that are present, but because one of these pairs is a lone pair, we end up with a pyramidal geometry of 107 degrees. Let's take a look at another example. So if we in its outer shell. So that must mean we need 2 hydrogens to obtain a full octet. So the total number of electrons around the central atom is 8, which gives us 4 pairs. So we would predict a tetrahedral shape with a bond angle of 109 degrees. So if we look at our structure here, we can see that we have our oxygen and we have 2 covalent bonds with hydrogen. So we have 2 bond pairs and we have 2 lone pairs here. So these lone pairs cause our bond angle to be distorted, and that creates a bond angle of 104.5 degrees. And a bond angle of 104.5 degrees gives us a geometry called V-shaped geometry. And this V-shaped geometry occurs due to the increased repulsion specifically from the lone pairs repelling each other, and then further repulsion from the lone pairs and the bond pairs repelling each other. So to summarise, our prediction was for water 109 degrees with a tetrahedral shape. However, the actual geometry is 104.5 degrees and it's V-shaped. So here's a little summary table for you with all of the geometries that occur depending on the number of pair of electrons that are present and the number of lone pairs. So if we have 4 electron pairs present and 2 of those pairs are lone pairs, we have a V shape of 104.5. If we have 4 pairs of electrons with only one of those being a lone pair, we have pyramidal of 107. If we have 4 pairs of electrons with no lone pairs, we have a tetrahedral shape of 109.5. 2 pairs of electrons with no lone pairs is linear, and then 3 pairs of electrons with no lone pairs is trigonal planar. So that's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.